It's a great honor or pleasure to be here, and I'll try to talk a bit about like a short history of array computing in Python. Even though I'm like way too young to have experienced all of that myself, I hope I can like somewhat summarize or show what's out there and what has been out there. And yeah, so this is just like a short table of contents of what we're going to talk about. And yeah, first we're just going to define a bit what array computing is, and then look at the history up to NumPy, and then look at what has happened after NumPy came around, where there are a couple of like really interesting pure Python libraries for different special cases, and then also JIT and ahead of time compilers, and of course there's deep learning. And then at the end, hopefully we'll finish with a new NumPy extension proposal that's basically soon to be merged. Just to define a bit what arrays are and why they are important. Arrays, I think all of you probably know very well that arrays are used in practically all scientific domains. Like for example, physics, controls, you see an image there or a point cloud. All of this can be represented in some sort of array, and that means that arrays form a very important basic to basically derive any information or computation of this data. And the idea behind array computing is to make it possible to express an operation that's usually defined on a scalar on an array as well. So for example, here is this like super simple operation a plus b that you usually, if you want to run this on arrays, you need to write your own for loops. However, with array computing, the idea is to generalize these operations to scalars, from scalars to arrays, and you can just write a plus b, and your for loops are implicitly done in the array computing framework. And I'll give a brief introduction of what an n-dimensional array actually is. So basically, an n-dimensional array is defined by some sort of memory region, which is usually a linear memory allocation in a computer. And then you definitely need to have a dimension, because that's really in the word, and a shape. So for example, here we see a row major array with a shape of 3 and 4, and then there's something called strides. And strides basically just are a tool to figure out from an index the location in the memory here, because this is what the computer has. So for example, if I want to go to the index 1, 0 here, I'll just take the inner product with the strides, so I multiply 1 with 4 and 0 with 1, and I end up with number 4, which is the offset in the linear memory. And we can quickly go over to Jupyter Notebook, where we can see this in action in the NumPy array. So if I create an array here, I can look at the dimensions, and then I can look at the shape, and I can look at the strides, which are computed just like I showed before, and I can see that at the index 1, 0 we have a 5. And if I look at the flattened memory, which is basically the linear memory that the computer sees, I can then take the inner product from the with the strides and the index here, and index into the flattened array, and I see that I end up at 5. And so yeah, that was a very brief introduction into what n-dimensional arrays are. And there's also the possibility to, instead of storing your array in a row major fashion, you can store it in a column major fashion, where your linear memory is basically ordered in a different way, and you have different strides here. And well, this all kind of started out, or one of the first languages to actually do something with array computing was Fortran, and it's the kind of translation of what Fortran means is formula translator. And that kind of shows how the idea behind this is to make a language that's really expressive, and array computing is one of the ways to make it easy to translate your equations into computer code. And Fortran is still a reference in benchmarks, and some of the original implementations of BLAS and LAPACK, for example, that are linear algebra subprograms that are still used by NumPy today, are in Fortran. And just to have an honorable mention of a pretty cool language that's called APL, which stands for A Programming Language. It's a seriously dense language, and it's like really has arrays at its core. And what you see here is a like entire implementation of the game of life in this language. And if you're bored with this talk, you can go to tryapl.org and check it out online. It's really fun. And they used to have these like specialized typewriters with all these crazy symbols to write this language. And then 1987 there was MATLAB, which probably a lot of people that have gone through like engineering education know. It's a proprietary software from MathWorks, and it was sort of as like a dynamic interface to Fortran for the students of some professor who started it, and it kind of pioneered interactive computing and visualization, alongside, of course, some other libraries and languages. And then 1991, Python saw the light of the day, made by Guido van Rossum, and they came up with a numerical package that's called Numeric in 1995, which was basically the first numerical computing package in Python, and that actually inspired some additions to Python. For example, the indexing syntax is has been inspired by the needs of this package. And Guido van Rossum, for example, was also part of a special interest group that formed around numeric computations in Python. And then in 2003, NumArray was basically a new edition of similar ideas to numeric. But unfortunately, it was slower for small arrays and better for large arrays, and that kind of led to a split in the community, where SciPy was still remained reliant on numeric, but other people started to use NumArray. And then in 2006, Travis Oliphant took it on, started to merge numeric and NumArray into what became first SciPy Core, and then branched out into what we know and love as NumPy. And it brought us fast and flexible array computing in Python with this core notion of having a typed memory block that's equivalent in the memory space to what we have in C or Fortran, and then this notion of broadcasting and vector loops that are written in fast C. And I'm just going to quickly talk a bit about what broadcasting actually is. So broadcasting is basically an answer to what you do when your dimensions of the n-dimensional container do not match up. And I'll demonstrate this again in the Jupyter notebook. So when we go here and we create two arrays that don't have the same dimension, because the first one is 2D and the second one is 1D, we can still do element-wise operations on them. And what happens is that the second array that only has one dimension is broadcasted to be equivalent to a two-dimensional array. So we just extend the dimension by prepending like a 1, or actually in this case a 2. So what we see here is that this element-wise operation still worked out. And another of the cool things that came around with NumPy are ufuncs. And ufunc stands for universal function. And universal function, all of the functions or a lot of the functions in NumPy are implemented as ufuncs. And ufuncs have a specified number of input parameters and a specified number of output parameters, and they have a signature. So for example, if you use numpy.sign, you go from a signature of float to float and so on. But the cool thing is that NumPy ufuncs are a very simple way to write functions that are generalized and that use this broadcasting mechanism and the NumPy casting mechanisms. And I'll quickly show you how you can write a ufunc in the Jupyter notebook or in Python. So here we see that np.add is actually a type of ufunc that's an add, and I can define just some array again, and now I can do np.fromPyfunc of this ufunky, which is just a simple add of x and y, and I define that it has 2 input parameters and 1 output parameter, and I just go, and I have already a function that's basically the inner loop of an array computation. So what I see here is the same result that I would get if I just do np-add, which is like the real NumPy function. And ufuncs go a step further, and they also, if you define a ufunc, you also get for free basically, for example, methods such as accumulate and reduce. So the functions that you usually know as np.sum, which is a reduction, you can express it as a ufunc. So the ufunc that I defined above also have this .reduce function, which applies the ufunc that, which applies this ufunky func in such a way that it reduces along the axis 0, which gives me the same result as doing the same with np.sum. Or I can use accumulate to basically get the equivalent of cumsum, which is pretty cool and very powerful. And all of this kind of made NumPy somewhat like a standard in the Python world. NumPy didn't really manage to become part of the real Python standard library, and I think at some point it was kind of the idea. Parts of NumPy have become part of the standard, like the Python memory view, but NumPy itself didn't make it. However, I think in the community we can all agree that NumPy is some sort of standard and the API is really well known. But with time, the needs of the users have somewhat shifted, and more specialized data containers were kind of necessary. And there are a couple of things that can be attacked. For example, parallelization, speed, the GPU, and the data size all increased or changed, and so on. And now we'll see a couple of libraries that basically implement the same API of NumPy, but for different purposes or with different trade-offs. So for example, one of those is numexpr, which stands for numerical expression. And one of the key idea here is that numexpr tries to avoid temporaries by evaluating the expressions in chunks. And when we look at the way how numexpr defines a computation, for example, down here, we see that we actually, to numexpr, we actually pass a string, and the string gets transformed into a bytecode for a specialized numerical virtual machine that will execute this in chunks. And this works great, for example, for large arrays. And then there's Dask. Dask is a library that also defines its own distributed ND array. And what you see over here is this entire thing is a Dask array. But a Dask array is actually a combination of a lot of smaller NumPy arrays. And what Dask does is it creates a big function graph and then distributes this function with a scheduler over a large number or potentially large number of machines. So if you have a cluster of machines, using Dask makes it very efficient and makes use of all these parallelizable routines here. Then there's a sparse container that's somewhat new, which is called PyData sparse. And it has support for sparse n-dimensional arrays. There used to be another sparse container, or there still is a sparse container, in SciPy, which is called SciPy sparse. But SciPy actually is only 2-dimensional, so it's just like a matrix. However, the PyData sparse array is really n-dimensional, and one of the advantages of sparse array is that you basically remove the storage for all of the zeros in your data. So if you have some data that has a lot of zeros inside, you can have a very good data compression and also faster computation if you use the correct algorithms. And here we can see how you can how data is stored in PyData sparse. So we store the index here and then the data. So we store an index for the row, for the column, and for the data, and so on. And here you can see that you pass just two lists with coordinates and the data, and that creates this diagonal array here. And PyDataSparse, again, follows the API of NumPy very closely, so people who are familiar with NumPy already basically know what to do and how to do it. Now, another trend that's happened is that GPUs are used for computation more and more. And GPUs offer a massive parallelization of your computations. And it's great for large data. There's a kind of a cost that you have to pay when you send your data to the GPU because it needs to be transferred from the CPU to the GPU. And it's a bit of a different programming model. But all of this is pretty well hidden behind QPy, which is, the Q in QPy stands for CUDA, which is the library that NVIDIA published for this general GPU programming. And it's basically the industry standard now. And QPy was developed as part of the ChainerDL framework. And when you look at the code here, you see that you can import QPy as CP, and then you just create the NumPy array, for example, here with np.arange. And when you do cp.sArray, it sends the array to the GPU, and then you can perform any calculations as you want on the GPU, and then send it back to the CPU by using cp to NumPy. And again, QPy also follows the NumPy standard pretty much. And one of the most recent developments in this kind of like array world is XND. And XND is a library that is basically created under the lead of Travis Oliphant again, who also was responsible for NumPy more or less. And it's not just one library; it's basically three libraries that are ND types, which is a shape, type, and memory abstraction library. Then GeoMath, which is responsible for dispatching math functions on memory containers. So that's basically the ufunc part of NumPy. And then we have XND, which is kind of the bridge to Python for those two other libraries. And ND types is a pretty cool library, I think, because you can do much richer abstractions, and your shape becomes part of your type, which can be really powerful. For example, when you think about compilation stages, when you know, for example, that you have an array whose shape is never going to change, you can enable a couple of very powerful optimizations. And I think XND is not very widely used yet, but I think it's a library that one could put an eye on because it could be really interesting. And now we're talking a bit about just-in-time and ahead-of-time compilers, because it's also something that kind of came out of the Python community in the need for speed. And we have a couple of really interesting concepts for just-in-time and ahead-of-time compilers, and I'll talk about two. And one of the most powerful ahead-of-time compilers that really works is Python. And it supports Python and NumPy interface. And it compiles this to C++. And it's a ahead-of-time compiler, which is different from a just-in-time compiler, in that you use a command line tool to first compile your code to C++ and then to machine code, and then use it import it as a module into your Python code. And it supports a bunch of high-level optimizations in Python, and it also has a bunch of optimizations in the C++ part of it, where it re-implements a bunch of the NumPy API. And nowadays it also has a Cython integration, which is pretty cool. However, Cython is also a Python compiler, or a Python-esque language compiler, which itself does not feature array computing. And here you can see how you use Python. Basically, you write the regular NumPy code, and then you add a small comment on the top that says Python export this function with this signature, which will then be picked up by the Python compiler to generate this super fast binary. Another of these numeric compilers is Numba. Number follows a bit of a different strategy in that it compiles Python to LLVM, and it's a just-in-time compiler, so it doesn't have this separate compilation step. Instead, you just use a decorator to just-in-time compile your code. And one of the other features that it has is that it supports GPUs with a pretty nice, rather high-level API. But it does not really support array computing too deeply. It uses NumPy for the array computing, so for high performance, people tend to write explicit for loops. So here you see what the number looks like. You have this @JIT decorator with a bunch of arguments here, and then you see this for loop, which is usually necessary to actually achieve like really high speeds and the loop fusion and these kinds of cool optimizations. And then another thing that you can do easily from number is to use the @vectorize decorator to generate one of these ufuncts that I showed before. Or you can use the @CUDA decorator to generate code that runs on a GPU, where you have a bunch of like pretty nice high-level features to do a CUDA.grid, and you don't have to mess with the things that are otherwise necessary in CUDA code, which is like thread indices and keeping track of where you are in your array. And the third trend that is happening in the ecosystem of Python is that the AI winter is finally over since a couple of years. And there has been this kind of like deep learning revolution. And the Python ecosystem has pretty heavily benefited from it. And lots of array computing have come out of it. And one of the basic principles that are used a lot in machine learning or these deep learning libraries is the computation graph, where you basically define your variables as input variables here, as A and B are just inputs that you can see down here in the computation graph. And then instead of actually doing the computation while you're reading this input, you just record them into a computation graph. So we see that C equals A plus B is this stage in the computation graph, and you have D equals B plus 1 is this part in the computation graph, and so on. So you basically record your computations, and then afterwards you can take the computation graph and execute it, and so it's kind of a symbolic abstraction of your numerical array. And things that you can do with the computation graph, and basically why it's used so much in the machine learning community, is that it allows for automatic differentiation, which is then used to improve your training results and so on. And there are also a couple of really cool optimization opportunities in using the computation graph, which is, for example, common sub-expression elimination, where you can figure out that you're doing the same computation at two different places in your computation graph. So you can remove one and just insert the result of one into the place of the other one. You can do some algebraic simplifications, for example, like removing the y here, because you see that you are also dividing by the y. Or you can do constant folding passes, where you see that you have a 2 times 3 and it never changes, so you just make it a 6. And you can fuse ops in inner loops. And I think one of the libraries that kind of pioneered this approach with a computation graph was Theano, and it featured this lazy evaluation, and then it compiled your computation graph into C and CUDA kernels. However, this library was killed by Google, kind of, because they released 1.0 like last year, but that was also the last release ever. And the people who started the library have now stopped working on it, and TensorFlow came around. And it's this big library from Google that follows basically the same principle and ideas of Theano, but did not, in fact, feature this compilation stage to C and CUDA at the beginning. And TensorFlow, yeah, I mean, it has a huge budget and a lot of people working on it, so it moves very quickly, and it added a lot of features. But just to look quickly at what you can do in the basic setup of TensorFlow and how you build up this computation graph that I was describing before, is you use a tf.placeholder here that defines your inputs, and you have some tf.variable which are states that you can extract. And then you build your computation graph down here, where you do some operation on your input and some more, and then you define a step, which is where you basically extract your values. And then you can use a TensorFlow session that executes this computation graph and pass the inputs here as some real numeric values. So that's like the very basics of TensorFlow. And TensorFlow came up with a thing called XLA, which is actually a compiler again. A compiler that supports JIT and AOT modes, and that also uses LLVM under the hood, and it's still in an experimental stage. But I think it could be a pretty exciting development because it lets you compile these TensorFlow graphs into very performant binaries. And another big library that's now in the Python world that basically kind of came from, I think, Lua, is PyTorch, which is a deep learning framework from Facebook. And again, it features a computation graph, which in this case is dynamic. And it's not this static, deferred graph model that we were seeing in TensorFlow, which makes it a bit easier to have dynamic control flow than with TensorFlow, where you need to insert specific ops at the right places to actually simulate something like control flow. And PyTorch also comes with JIT and TorchScript. And TorchScript can compile a subset of Python, which includes, for example, stuff like lists, NumPy expressions, and a bunch of other things that are compiled into machine code, and that can generate, again, CUDA and CPU code. And here we can see how we can use the torch JIT to actually translate this Python inside of this function into a very performant binary. And now we can derive some conclusions. What we've basically seen here is that NumPy is the best API, at least, and that there are now many like different NumPy implementations out there, which all have kind of their special case in the ecosystem, and there are a lot of downstream projects that depend on the NumPy API in some sense. So for example, Pandas and Xarray and Scikit, the various tools, they all use NumPy in some sort. And 6 months ago, there was a proposal started by Matt Rocklin, based on a blog post that he wrote, where he describes the problem that it became harder and harder to write generic code. And what does it mean to write generic code? So for example, we have a function here, that's f of x, and that's doing some stuff inside where it uses some sort of NumPy API. So for example, we're doing y equals mp.tensor.x and x transpose, and then return the mean of the exponential of y. And so if your input to this function is a NumPy array, this is totally fine. Because then you just do your NumPy tensor dot, you use your transpose, etc., and you get out a NumPy array. However, if your input to this function is let's say a QPy CUDA array, you'll get a problem. Because NumPy here calls tensor dot on these inputs, and it doesn't know what to do with QPy array, so it will either throw an error or NumPy also has means to basically try to make it a NumPy array. And that's kind of sad, because it would be great if we could just pass in any x that follows the NumPy API, and it would just like magically work. So they came up with this array extension proposal, which basically lets the arguments of the function take control over the function itself. So if the argument x here defines a magic underscore underscore array underscore function method, it can select the implementation itself that's going to be used for the tensor dot. And that's a pretty powerful thing, because it allows the users to write generic code and then pass in any NumPy following library that the user wants. And the same is already true for the ufuncs I showed, because there's already an array ufunc extension point. And I think that's going to basically help to bring the ecosystem again back together onto this like NumPy kind of standard implementation. And if you're interested in this, this is probably going to show up in NumPy 1.16. And there's this NumPy enhancement proposal number 18, where this array function protocol is described. And yeah, let's just have a last look about some concluding trends. The ecosystem has become a lot richer in the past years. We see a lot more interest in like actually compiling Python or Python-like code into something really fast. And there are more specialized NumPy implementations for different ideas, and the array function will make it easy to write implementation-independent code. And with that, I'll conclude. Thanks a lot for showing up. And I'm actually working on this extensor project, which was mentioned in the beginning. And we are trying to do the same as NumPy, but in C++. So it's yet again another idea, or re-implementation of NumPy. Yeah, and thanks.
Thank you, Wolf, and thank you for staying on time. So we do have time for some questions and comments.
So first, thanks for the great talk and the great historical retrospective of array computing. Then can you go back to the slide about algebraic simplification? The one where you say that x times y divided by x is equal to y. Yeah. So it's scarcely true. Compilers can't do that, because if y is equal to 0 in one element, then you don't have x. If it's a floating point number and you've got some not a number, then you're doomed too. If it's an integer and you've got wraparound arithmetic, then it's false. So people tend to think that algebraic simplification are a good thing for compilers, but if they are to follow the floating point spec, then there are very few simplification you can do. So that was the first comment. So don't use -o fast, basically. And the second one is, can you give us an hint about why do NumPy need compiler to speed up its computation? What is the problem with NumPy at that point?
Does this work? Oh, wow. Why does NumPy need compilation? Okay, that's a good question, actually. I think, or I mean, my opinion on this is that the Python is a really amazing language, but it's super dynamic. So basically, everything you do in Python needs to go through this runtime and check for example, if the plus operator is overloaded, if the multiplication operator is overloaded, and so on. So there's a kind of a huge cost that is paid in this dynamic language, where a lot of the assumptions that you can make in static languages are not true anymore. And that's the big price that you pay when you use NumPy directly, because you retain a lot of this dynamicism if you don't like properly vectorize your code. For example, if you write for loops in Python, it kind of is very slow compared to for loops in C or C++.
Thanks.
Yeah, if I can add something, there are issues with copies in memory. Yeah, NumPy does too many copies for nothing sometimes. If it were more intelligent, it would not do the copies, and that's something that numexpr, for instance, optimizes. It takes time to copy a big array. Another question or comment? We had both. That was good. Thank you. All right. All right. Thank you again, Wolf.